All right. So we have finally arrived at chapter 12, which is the very last chapter of AP Statistics. And the approach that I choose to take with our last unit here is we do an extremely shortened, abbreviated version of the chapter where we just hit on a few highlights. There's a piece to chapter 12 that I'm not getting into in these videos, and we'll talk more about that in class later on, or I'll probably reference it in a future video. But the purpose of this first video here, before we can dive in with the new stuff, chapter 12 actually ties in with chapter 3, which we did a long time ago, which was all that stuff about linear regression, residuals, R squared, least squares regression line, all of that stuff ties into what we're going to be doing in chapter 12. So in this first video, before we can jump into the new contents, we're going to review all the stuff we learned in our regression chapter. This is kind of nice because the timing of this is pretty close to the AP test. We're about a month out or less by the time you guys are actually watching this video here. So we get to practice one of the biggest chapters of the book and one of the ones with the most pieces to memorize right before you actually need it for the AP test. So the context of our problem today, we are looking at whether the row that you sit in a classroom has any sort of impact on your test scores or your students' achievements. So what you'll see right here, row 1 on the x-axis here, row is my potential explanatory or x variable. Row 1 are the kids who sit really close. Row 2 sits behind them, 3, 4, 5, all the way to row 7, which is in the back of the classroom. We've got our scatter plot. We've got our raw data over here, and we also have all of the computer output that we need to make our regression line. So the first question asks us to describe the association shown in the scatter plot. And as a reminder, back in chapter 3, our 4 letters for this, we went FUDs with it, I think is what we decided on. F stands for form. And when we talk about form, we're talking about linear versus nonlinear. U stood for unusual points. So unusual points being sometimes outliers, but also those high leverage points are things that are just different than the rest of it. D stands for direction, positive versus negative. And S is going to stand for the strength. Whether it's strong, moderate, moderately strong, weak, whatever it may be, or no correlation at all. So when I look at this picture right here, I'm not going to write this out in words, or maybe I will. I'll pause it and just throw it up there for you guys. But when I look at form, the dots in this picture are just like a cloud. There's really no good pattern going on with my data right here. They do attempt to put a blue line through the data, but like, is this data any sort of a pattern? It doesn't look like it to me. You could make the argument that it's somewhat linear. It used to be this way. Somewhat linear, like it's going a little bit high to low, but not even really. If it is, it's extraordinarily weak. With the points being so all over the place, I'm not sure it really makes sense to talk too much about unusual points. Perhaps this kid who sat in the back of class and got like a 60 on their test, that's a little bit off. But when the data is just so spread out and all over the place, that one point maybe isn't even worth mentioning as something particularly special. Direction, you could perhaps make the argument it's very slightly negative. That's what the least squares regression line is going to try to tell us in a minute. The strength is extraordinarily weak, if not no correlation at all. So I'm going to write something up like about this, talking about it being super, super weak rather than no correlation, so we can practice that. But there's not much going on between the row and the scores on the tests. All right, so I've got a little sample explanation right there. I chose to put it as very weak or extraordinarily weak rather than just saying no correlation because I wanted to practice the little script you would write afterwards. So I mentioned weak, I mentioned negative, I should have mentioned linear. I did not put that word in there, so I'm going to throw that in there right now. Is this linear? Not really, but it's not like it's anything better. So like a line is going to do as good a job as anything. with a data set like this. So I would say those things. I mentioned my variables, and then that sentence of context afterwards, where as your row gets farther back, your score may go down a little bit. There's not a lot going on between these variables, which makes sense. Kids who sit further back, like, it doesn't automatically mean they're going to be doing worse on their tests, so that's not terribly surprising. Number 2 is asking us to use the computer output to make the equation for our line of best fits. Now, when we did this back in chapter 3, we did learn how to do that on your calculator, doing stat edit and everything, linreg. And you may be asked to do that, but it's a lot more likely they will give you computer output. They don't want to risk a kid typing a button wrong, typing one of the numbers wrong, and not being able to get the same answer. It's just easier to give kids computer output so everybody's on the same page. Now, when we learned about this way back in the day, a few of these columns we kind of crossed out. First of all, R squared adjusted we will never use. We don't use the adjusted version. It's going to be just normal R squared. The T and the P, we just scratched that out before, like, oh, that doesn't matter. A little bit of foreshadowing here. P stands for p-value. T is a test statistic. It's going to be a T. We'll learn about that in the next video when we jump into chapter 12. But we're not going to scratch those out this time because we actually will start to look at this. We've got S, which we would use. But the info you need for your line of best fit is this first group right here. This is my X variable, rho. So this number, the coefficient, is your slope on the X. The constant is your y-intercept. So if I was going to write the equation, I like to do it with the words from the problem so I don't have to define my variables. My predicted score is going to equal, and we like to put the y-intercept first, and then it would be minus 1.1171. And instead of writing x, which I'd have to define, I'm just going to use the word rho. You could do y hat and x, but you would have to define them separately. So that's going to be the equation of that blue line that you guys can see on the scatter plot. Next up, they ask us to find the value of the correlation. Correlation is going to be R. And in this problem, they tell me R squared is 4.7%, which you do have to turn into a decimal, move it 2 spots, 0.047. So what I would need to do on this problem is take the square root of 0.047, which is about, if I square root both sides here, you're going to get R is approximately 0.217. But you have to remember to look at the problem and decide if R is positive or negative. In this particular problem, it is a negative line of best fit. My slope is negative. So I need to remember to make my R a negative value. So R is about negative 0.2, which is in the very weak category. So that's my correlation. Next up was the concept of a residual. And residuals, if you think back to a long time ago, I taught you guys residuals, the way you find them. It's AP. You are in AP statistics. A is the actual Y value. P is the predicted Y value. So this is what you do to find a residual. So when I set that up for my problem right here, I want a student who scored a 76 sitting in row 1. That 76 is their actual score. It's what happened in real life. And I need to subtract out my prediction, which is going to be me plugging a 1 into my equation right here. You've got to plug a 1 in to that LSRL equation. So if I do that for this problem, I have to do 85.706 minus 1.1171 times 1. Looks like I get 84.59 if I round that. And if you subtract those two quantities there, you're going to end up with a residual of about negative 8.59. It also asks us to interpret our residual. So you have to think actual minus predicted. I have a negative. That means my predicted was higher. So you can talk about how the actual is lower than the predicted, or you can talk about how the predicted is higher than the actual. It can work either way for your interpretation here. So what I would say is that a student who scored a 76 in row 1 scored 8.59 points lower than we would have predicted using the LSRL. Or I could flip it around and I could say instead, hey, we predicted 8.59 points too high compared to what this student actually scored. I like my first method better because it's a negative, so I like talking about it being too low. That just makes logical sense to me. So I'm going to pause and put that script up there for you guys. All right, so we got a little script up there for our residual. Next up is another script. Chapter 3 was the chapter full of different interpretations you need to remember. When we talk about interpreting the slope, our slope in this problem was going to be this negative 1.1171, which you should always think about your slope as a fraction, rise over run. So for every 1 unit increase in x, the run is a positive 1. Your y is predicted to decrease or increase. This problem is decrease, though, because it's negative by that. So what I would say in my problem in context, for every 1 row further back a student sits, their test score is predicted, put that word in your interpretation, to decrease by approximately 1.1 points. All right, so there is our script written out for the slope of your LSRL. Next thing we need to do is interpret the standard deviation of the residuals. That was S from our problem. This is also going to be a script. So remember the idea of a residual. Residual tells us how far off each point is from the line of best fits. Some of them are positive. Some of them are negative in how far off they are. But if you were to average the length of all these purple lines here for each individual dot, you will get S. S is a distance, and it's going to be measured in the units of your y variable. It's a vertical distance here, which is y, which is score. So when using our LSRL to predict score, based on what row you sit in, our predictions will typically be off by about S, so 10.06 points. If you average all these purple lines, they end up being about 10 in length. So our predictions are typically going to be off by about 10. That was a script you all should have memorized. It's been a little bit, but I will throw that up there for you. All right, so there's our script for S. Next up was R squared, also a script. R squared in this problem was 4.7%. So the whole script you guys were supposed to memorize for R squared. Maybe pause me, see if you actually remember this, because it's something you do need to know for the AP test. But what you would be saying here, out of all the reasons why score might vary, why would our predictions not have been accurate for this problem? Well, there's a lot of reasons why you might get different scores. How much you study, how much you naturally understand, how good of a test taker you are, how distracted you were, etc., etc. Out of all those reasons, the row you sit in explains about 4.7% of the variation. In other words, that's terrible. The row you sit in has very little to do with why you might get a certain test score here. So the actual script talks about how 4.7% of the variation in y, in test score, is accounted for by the linear model which relates test score to the row that you sit in. Okay, so I'm gonna put that script up for you all. All right, so there is our script for R squared written out. Again, S, R squared will be on the AP test. Memorize both of those. It's been a while since you've been forced to think about them. The next two questions right here are just review of experimental vocabulary. Now that we're getting towards the end of the year, we got to start remembering all that experimental design stuff. What is the purpose of random assignment? Why did the teacher randomly assign their kids to their seats rather than allowing them to sit where they want to? The answer to that is you want your groups, for the rows or whatever, to be as even as possible. If students were allowed to choose their own seats, you may have groups of friends gravitating together. You may have the high achieving students who all want to sit in the front of class, etc., etc. Your groups are no longer equal, so you can't make any sorts of cause and effect claim. Random assignment creates equal groups, or approximately equal groups, so you can test that your variable actually is what's making the difference. I won't put that in words, but that's on the paper, but that's basically what we're looking for there. It allows us to make cause and effect claims because it balances our different groups. What other variables did the teacher control? The teacher did this on a specific unit. They used one chapter, and they used the same chapter test for everybody. If the teacher had just done this over the course of a semester, just give me stuff when you guys feel like it, and just did like dumb things like that, our results would have a lot more variability in them, and then we wouldn't be able to tell what was up. So they used the same test, they used one unit of study, they did it in the same class, they didn't compare row 1 in this class to row 6 in a different class. So they kept those other variables the same for the hopes of limiting variability in the study. Even with the variability limited, like you saw, the results are not very good or promising in this study, but that was the purpose of control. So basically limiting variability caused by these other variables. Two questions right there that are just nice review of experimental design. So number 10 brings back our friend, the residual plots. And with a residual plot, what they essentially do is they take a scatter plot like this, all my little purple lines right here, and they take those purple lines and they graph them and sort of flatten out the picture. So we can see better how much our points are off by. Remember that a residual plot is the only way you can determine whether a linear model is appropriate. And we want to see random scatter. Scatter means the line is doing as good a job as anything. If we would see like a big curved pattern here to our residual plot like this, that would tell us a line of best fit probably isn't the best call. So in this situation here, a line seems to be doing a pretty good job. It's just random scatter that I'm seeing in my residual plot. So yes, a linear model is appropriate, only random scatter. There's no leftover pattern in the residual plot. Had we seen a pattern, then we would say, hey, a linear model probably isn't the best fit. Again, don't confuse this for saying, oh, the line's going to do a great job. It's totally not. This line is terrible. It's not fitting the data very well at all. A line is just as good as anything, basically. That's what a residual plot does. It tells you if there's a better choice than just using a line of best fits. And that takes us for this video to our final question here. We are going to move on and start to analyze our line of best fit using all that significance testing HOHA stuff. That's where chapter 12 is headed. So when we look at this problem here, we basically are trying to decide if there's actually going to be convincing evidence that your row causes lower scores, not causes necessarily, but is associated with lower scores. You guys saw in this problem, the row didn't seem to do a super ton in terms of like, oh, is it helping scores? Is it hurting scores? There wasn't a very strong association at all. But what we work towards in chapter 12 is figuring out if we get a line of best fit, is that line of best fit convincing enough that we know there's a relationship going on? So this last question right here, does the negative slope of our regression equation provide convincing evidence? We will see in chapter 12. That is what we're building towards. Is our line of best fit strong enough or convincing enough that we can actually say something's for real up with the two variables, that there's a relationship there, and that it's not just some random fluke. So that is what we will do in this chapter.